All right, so now I'm going to introduce you guys to the periodic table. So let's just take a look at it here. This is a fairly intimidating looking thing here, the periodic table. But first of all, let's just take a step back. What the heck is the periodic table? A periodic table is an organization of all the different types of atoms on Earth, right? So this is all, let's actually say all the different atoms on Earth, or actually anywhere that we humans have discovered. It could be that some faraway place in the galaxy there are more atoms, more different types of atoms, and so their periodic table would be bigger. These are the ones that us humans have discovered. These are all the different types of atoms. So actually, if you think about it, it's kind of crazy that the world is composed of just, a maximum of 118 different types. And even then, it's actually way smaller than that in terms of like, this thing doesn't exist anywhere, basically. I mean, it was probably made in a lab by some scientist at some point, but it's not like you're going to find it in the ground. So in terms of the atoms that we actually interact with in our daily life, it's a tiny subset of this table. Okay, but that's what a periodic table really is. It's just a sort of display of all the different types of atoms. And it's organized in this way for a reason, okay? And we'll talk a little bit about that here in a second. First of all, let's go for the basic organization. The most important sort of feature of the periodic table is, if we zoom in, you'll notice that everything is given a number. That number at the very top. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it just keeps on going all the way to 118. There aren't any gaps or anything like that, right? There's no doubling up of this. This is, again, in purple, this is what we call the atomic number. It's often represented by Z. So for example, Z equals 6 would correspond to this element right here. So this would be equals 6 equals carbon, etc. So each element has its own atomic number. Okay? Now, the other thing about the atomic number that's kind of crazy is that the atomic number equals the number of protons that that element has. So again, if we look at carbon here, right, here's carbon. Its atomic number is 6. That means that every carbon atom has 6 protons. That's what makes a carbon atom, is having 6 protons. If I add a proton such that it has 7, it's no longer carbon. Now it's a nitrogen atom, right? If I take one away, it's no longer carbon, now it's boron because it has 5 protons. So the number of protons is what uniquely determines what element is what, right? So for example, which element has 10 protons? Everybody take a second looking at your periodic table and see if you can't tell me. All right, so we can just sort of go down the line with the numbers if you're having trouble finding it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So neon is the element with 10 protons. Again, if I added a proton, it's no longer neon. Now I'm going to have 11, so I'm going to be sodium, et cetera, right? So this atomic number, it's sort of organized by atomic number, the periodic table for increasing atomic number. But that atomic number is equal to the number of protons that that element has, right? Again, number of protons is what uniquely determines what element is what. Okay. One thing I want to say about this periodic table is, you guys are new to chemistry. This is your first time sort of looking at this periodic table. It's going to kind of suck at first to have to hunt down like where chlorine is. It's something that you will get better at with more practice. At first, you're just going to be looking at this thing, trying to do your best to find it. It's going to be kind of frustrating at first. And then by the end of it, you'll kind of know, oh, chlorine's going to be on this side of the periodic table somewhere. Ah, there it is. That's just a skill you're going to have to get good at. But hunting down certain elements, finding them is really important. Okay. The other thing that we'll notice about this periodic table is everything has, so we covered atomic number, right? The other thing to notice is that they have both what's called the atomic symbol, which is in the case of carbon C, and then of course the name of that element here, carbon, right? So basically every element has been given this shorthand symbol, and that's really just because scientists are lazy, and we don't want to have to write out, for H2O, which is water, we don't want to have to write out hydrogen, oxygen, or something like that. We want to be able to abbreviate it as H2O, right? So that's why we have these chemical symbols. And again, it's going to be a really big pain in the butt if I said, how many protons does the element Fe have? You're going to have to hunt on this periodic table until you find that atomic symbol. Turns out it's right here. And so you know that Fe has 26 protons. It's just something you're going to have to get used to, have to get good at. Okay, so let's just do an example here. We got to identify the element with atomic number 16. Okay, so everybody take a second and see if you can't identify the element that has atomic number 16. What is its symbol and what is its name? Okay, so if I'm looking for the element with atomic number 16, that's right here. So that's S for sulfur. And then the last question I could ask is, how many protons does sulfur have? Again, you got to know that that atomic number is the same thing as number of protons. So it has 16 protons. All right. So again, I said that the periodic table is the summary of all the different elements that we scientists have discovered here on us humans have discovered. If we looked at the human body, we would see that it's really composed of only a majority of 6 different elements, right? So most of what our body is composed of is oxygen. That's because we have a lot of water in us. The other main part is carbon. There's also a lot of hydrogen, again, because there's a lot of water in us, nitrogen, and then we have calcium and phosphorus as well. But all those together make up, all other elements are only 1.5% of our atomic, our body mass, right? So 98.5% of your body is consisted of just 6 different elements. And we can look at the Earth's crust as well, and it's kind of a similar story. It's not the exact same makeup, but you can see that, how many we got here? So oxygen, silicon, 1, 2, 3, 4, 5, 6, 7, 8 different elements compose 99.2% of our Earth, right? Again, we're mostly oxygen as well as a lot of silicon. This is, I think, specifically within the Earth's crust. So it might be surprising that there's a lot of oxygen in the ground. That's not oxygen gas. It's actually like oxygen that's bound to other metals within rock. So actually rock consists of a good amount of oxygen. Of course, there's all different types of rocks. This isn't a geology class, but yeah, I mean, it's kind of crazy to think that we have 118 known elements, and yet 99.2% is composed of these, what did I say, 8 different elements. Okay, so this is exactly the kind of thing that I would expect you to be able to fill out at the end of this lecture. And this is just your ability to hunt that periodic table, right? So whether you're given the name of the element, the symbol of the element, of, or the atomic number of that element, you should be able to find it on the periodic table and fill out the rest of that information. So let's actually start with atomic number first, because that's kind of the easiest since the table's in that order. So atomic number 13. So what are we going to do? We'll go back to our periodic table. There's a bigger one here. And we need to hunt for the element that has atomic number 13. So actually, it's a really good idea to pause the video and see if you can't complete that table on your own. And then you could play it back and make sure you're correct. But yeah, I'll go through it. So first of all, we're looking for atomic number 13. That would be this guy here. So the name of that element is aluminum, and the symbol is Al. All right, so we can go over here. Okay, so when it's the atomic number, it's probably the best case scenario because you can start looking line by line. Calcium, so now we got to find it based on the name. This might actually be the hardest because they're the smallest, right? So now you just gotta hunt. I mean, that's really the only thing. Once you get a feel for it, obviously me having been studying chemistry for almost 20 years now, I know exactly where to look. You guys don't necessarily have that yet, but with practice, you'll get a sense for where certain elements are. And because like we just showed, the human body consists of 6 and the Earth 8, you tend to talk about the same ones over and over again a lot, right? Carbon's a really common one. Calcium is actually a fairly common one as well. So in this case, hunting around our periodic table, calcium is located right there. It's got the symbol Ca, and its atomic number is 20, which is again the number of protons within every calcium atom. It's 20. Okay, so I'll leave you guys to do copper on your own. Oh, I just told you, but yeah. So Cu is copper, but you can try to hunt it down and find out what that atomic number is. All right, so now let's talk about why the the periodic table is still kind of funky looking in that it's got this weird kind of staircasey cutout thing. It's not just a solid block. So why is that? It's organized into horizontal rows called periods, but I think more important is the vertical columns, which are called groups. And so again, the vertical columns are groups. And why are those important? Because elements in the same group behave very similarly. Okay, so if I zoom in here, let's take this group right here. It turns out that oxygen and sulfur have very similar reactive properties, way more similar than oxygen and fluorine. Fluorine's right next door here, right? So even though fluorine is only different from oxygen because it has one more proton, it doesn't behave the same as oxygen at all. Whereas sulfur, which has 8 more protons, behaves very similar to oxygen, right? So these groups are really important. They sort of, things are grouped by reactivity, basically. If things share the same column, that means that they have a lot of the reactive properties of one another. And because of that, these groups, some of them at least, have their own special names, okay? So the first one here is called the alkali metals. I actually don't know if hydrogen's included, so we're gonna say it isn't. These are called the alkali metals. Okay, so you're gonna have to know which columns are associated with which name. That's another skill that I'll expect you to have. And again, that first one are the alkali metals. And so again, all alkali metals behave very similarly. Lithium behaves very similar to sodium, behaves very similar to potassium, et cetera, et cetera. Same thing with our next column, which are the alkaline earth metals. And that is this block here. Okay, and again, all alkaline earth metals behave very similarly. So that is why they're sort of been grouped in this same column. We have the chalcogens, which I've honestly never heard in my life, so I don't think they're terribly important. But apparently that's this group here, are called the chalcogens. Let's file that away in the back of our mind for the ACS exam, although again, I've been able to go 20 years as a scientist without having to ever know that, so I'm going to say out of all of them, that's probably the least important. We have the halogens. This is an important one. You'll hear about the halogens a lot. And that is the second to last column here. Fluorine, chlorine, bromine, iodine. Those are the halogens. And then last row is the Nobel gases. Okay. These are, again, they all behave very similarly. They're actually not reactive like at all, which is surprising for an element. So that's part of why they're grouped together. And that's why they're called the noble gases, because they stay all by themselves. They ignore everybody else. And then the last important group is the big chunk in the middle, which are called the transition metals. That's this big chunk. This big chunk right here. Okay, this chunk at the bottom, they also kind of have a special name, the lactonides and the actinides or something like that. They are very rarely talked about because they're just so unusual. I mean, they really are, like, generally speaking, the vast majority of the periodic table that you'll ever deal with in your life is contained within these first 4 rows. Everything below that is fairly rare. And there are some exceptions. Gold is sitting down here, mercury's down here, you have uranium. But even then, I mean, uranium we probably wouldn't even talk about if it wasn't so important for like nuclear fuel, because there's very little of it on Earth. And the same can be said of a lot of those other elements. So I'm not saying you have to ignore them completely or anything like that, but you'll notice that we don't really focus on that portion of the periodic table very much. All right, so now there's another sort of classification that we can talk about with our periodic tables, and that is metals, non-metals, and kind of this in-between category called metalloids. The vast majority of the periodic table, everything that is shaded in green on this periodic table, are the metals, right? So that's everything here, including this. These are metals. Okay, so there are many different types of metals. And yeah, that's actually the majority of the elements out there. In blue, we have the non-metals. Okay, generally speaking, the metals are really important in inorganic chemistry, and the non-metals are really important in organic chemistry, right? So carbon and oxygen, those are in the non-metals section. And then in the middle, we have what are called the metalloids, and they sit kind of on this zigzag here. And they have properties of both metals and metalloids. So they're kind of this gray area between the two. Okay. So in addition to being able to identify, first of all, where something is on the periodic table, what's its atomic number, its name, its symbol, etc., you should be able to categorize them if they fall into one of the categories we talked about, or be able to identify them as either being metals, non-metals, or metalloids. Okay, so let's take, I'm not going to do all of these, but let's take an example here. Let's do chlorine. we're going to characterize it as a metal, non-metal, or metalloid, and see if it falls into one of those categories that we talked about when we were talking about the groups on the periodic table. So let's go back to our big periodic table here and see if we can't figure out chlorine and where that is. Okay, so everybody take a second, see if you can't figure it out. I think we've already talked about it once, so this may be an example of where you kind of have an idea of where to look already. All right, so here's chlorine on our periodic table. Is it a metal, a non-metal, or a metalloid? All right, so chlorine. It's got a simple Cl. How many protons does it have? It's got 17 protons. It is a non-metal. And does it fall into any of the special categories that we talked about? It actually does. This is a halogen. Okay, so you want to flashcard those different groups that we talked about to make sure that you can identify which column is which on the periodic table. Okay.